Hello everybody. So, today we are back with fluorescence spectroscopy again. In our last lecture, we discussed this energy transfer, particularly in reference to Foster resonance energy transfer, that is FRET. So, today we will extend a little bit on this again, I mean this energy transfer again, and then we will switch on to electron transfer, that is another mode of quenching of fluorescence. So, actually quenching of fluorescence, I mean the monitoring of this fluorescence quenching is a very important aspect relating to photophysics, photochemistry, then chemistry of biomolecules, I mean related to many aspects. So, that is why we are going to spend a little time on this aspect, I mean this energy transfer and electron transfer. As I told you in the earlier piece of lecture, that this energy transfer in case of this Foster type, that is the Coulomb interaction, that is it is a long distance interaction. Using that, we can actually find out the distance between the fluorophore and distance between fluorophore donor, I mean donor and the acceptor. So, so that we I have shown, I mean I have given you the idea how this can be utilized to find out the separation between this donor acceptor pair, and how other factors are also important, like this orientation factor, then also the distance factor. I mean distance is there, it is r to the power -6 dependence, 6th power of r. Okay. And the characteristic distance I also have talked about. Now, energy transfer, as I told you that I discussed this Foster, that is dipole-dipole interaction mechanism, that is also known as this Coulomb mechanism. Okay. I mean this is one of the two mechanisms, and the other mechanism is called the collisional mechanism, which requires, I mean this energy transfer requires the real collision. I mean in that case it is a coupled exchange mechanism, I mean double exchange of electrons that occurs. So, Foster dipole-dipole interaction model I have discussed already. Now, here what is happening, that you see that this is your donor, you first excite this to D star, then D star, depending on the nature of interaction, I mean whether it is a dipolar interaction, dipole-dipole interaction, or it is an electron exchange mechanism, but still I mean the D star should interact with the ground state A, giving rise to D plus A star, and here it is called the energy donor, and the other one is called the energy acceptor. Now, in collisional mechanism, which is called the Dexter, now in this case, I mean in case of Foster, the oscillating dipole of D star creates an electrostatic field or an electrical field, which induces a transition between I mean A to A star when D star deactivates. So, that is the basic idea, that this oscillation, I mean oscillating dipole induces a dipole, I mean electrostatic field over here, and that, I mean it is basically a coupled transition. You think of a coupled oscillator, or you think of a coupled pendulum, where if you allow one pendulum to start oscillating, then if that is connected, I mean there is a coupling mechanism, then it will slowly get transferred to the other. Okay. So, that this first pendulum which was initially oscillating will stop and the other one will go up. So, and this is called your energy transfer mechanism. So, classical example is that. So, it is a coupled transition. In one case the D star is deactivating and A is getting excited. Okay. So, basically you have like a coupling method by which, I mean this is one pendulum, this is another pendulum. It is a purely a classical description. So, it will initially oscillate and then slowly this oscillation will be percolated to this. So, it will start to oscillate, okay. It will start to oscillate and it will stop. So, that you can think that the energy is transferred to this oscillator. Okay. So, here I mean in this Foster mechanism you can think in that way, I mean in that classical way. So, now now freight does not imply that two reagents or the two molecules collide in order to exchange energy. The process occurs at some large distance. So, it is not that as I explained to you, that there has to be a overlap of the emission spectra and the absorption band of acceptor and the emission spectra of the donor, but that does not mean that they will have to come, so that this some overlap must be there, is there. It is not like that. So, actually this is your Foster mechanism, and there is another mechanism which is called, apart from this Dexter, there is another mechanism which is called your trivial mechanism, and that trivial mechanism is like you have got in, I mean that you can call that as a radiative mechanism, that you I mean you get a D star and then it will emit, and this emitted photons will be absorbed by this nearby acceptor, I mean energy acceptor, so that it will get excited. So, that's a trivial mechanism. In that case it involves absorption, I mean emission and reabsorption of photon, but here in this Foster case it is not like that. Okay. Dexter mechanism, that requires D star and A exchange electrons in course of energy transfer process. Okay. So, that means, I mean if you just have a diagram like this, that you have in one case you have, say, donor, you shine with radiation, you have this. So, singlet, donor, then it will be D star, singlet excited, so that it will be like this. Okay. Then, so it is your D star, this is D. So, this is a course, I mean this is excitation process, and then you have an acceptor whose energy I mean energy gap is matching exactly with the energy gap of these two levels. Then you can think of this, and you have got so that this electron will be transferred to here, so that it will generate your ground state D. So, this is your A. Okay. So, this is your initial state, D star A, this combined description of the system. Then what you get is this, like you have this. So, you have your D back to the ground state, and you have this. Okay. So, in the first case, when it was the case of Foster type of energy transfer, in that case electrons are not exchanged. I mean, the coupled transition, what is happening by means of dipole-dipole interaction. So, this electron comes back over here and this electron gets excited to here. So, in that case electron is retained within the donor and acceptor, but here electrons are exchanged between the donor and the acceptor. Okay, so this is a typical diagrammatic representation of this Dexter, and so that means in order to have this exchange means in order to have this exchange of electrons, the interacting orbitals, I mean these two, I mean donor and acceptor, these two substance should, or these two molecules should come in close proximity to each other, so that there is overlap of orbitals, overlap of the electron distribution of D star and A, so that there is a transfer of electron, I mean transfer of electron from, I mean there is a, so that the coupled transition may take place. And this mechanism, I mean looking at this, you can think of that this mechanism is operative at short distances. So short distances. On the other hand, in case of Foster, it is long range, say of the order of say 50 angstrom. Okay. So, that is the so it is long range and this is a short range description. Okay. And you can imagine that as the distance between this increases, so this end to end distance, I mean between the donor and acceptor. So, as this distance increases, therefore, this overlap probability will also be reduced. So, it will rapidly fall, I mean it will rapidly decrease or decay this this energy transfer efficiency, or this rate rapidly decreases as this separation is increasing. So, it may be exponentially decaying, I mean it should decay very fast. Okay. Okay. So, so you see that these are the acceptor orbitals, these are the donor orbitals. So, there is a transfer. So, if this acceptor orbital is somewhere over here above this, then it may be difficult, because it is an energy demanding process. So proper matching of the donor and acceptor orbital is very important over here. Okay. So, it is a diagrammatic representation of the short range interaction. Okay. So, exchange of electrons, as I told you that this means exchange of electrons. Exchange of electrons. Exchange of electron means, I mean orbital overlapping is important. Okay. So, overlapping is, if this is important, that means distance between D and A is very important. Okay. So, if you think of this Dexter energy transfer rate Kd, then Kd will be equal to some constant into exponential to the power minus beta r. So, K Dexter is equal to some constant into exponential to the power minus beta r, where beta is some attenuation factor. Attenuation factor means it is kind of like some kind of shunting effect, as you heard about in physics, that how much it is attenuated. Okay, attenuated means it is impaired. So, I mean it is given some kind of resistance. So, that is called the attenuation factor. So, and r is your end to end or edge to edge distance between this donor and say acceptor. So, this distance. Okay. And naturally, you see, since it is exponential, so that means with distance it rapidly falls. So, that means it will fall exponentially. Okay. So, this is kd with say r. R means end to end or edge to edge distance between the donor and the acceptor. Okay. So, that is about this electron exchange. So, when the electron exchange mechanism is operative. So, transition metal complexes undergo energy transfer via Dexter mechanism, that is exponential to the power minus beta r, and porphyrins in singlet excited state does via Foster mechanism. So, these are typical I mean example. I mean you can find find plenty of example in literature and also in books. Like for this I mean these chapters, these topics what I am talking about, you may consult this J.R. Lakovich's text. Text, then by that is fundamental of fluorescence spectroscopy, then molecular fluorescence by Bernard Valure, then another fluorescence book by, I think it is also fluorescence spectroscopy by Albani, then molecular photochemistry by Nicolas J. Turo. It is a very famous text. So, these are the books. Apart from this, you can look for various journals, I mean which are referred in these books as well, like American Chemical Society's journal, I mean Elsevier journal, then maybe Royal Society of Chemistry journal, ACS, then RSC, Elsevier. Okay. So, these are the the journals from this society you can look into. Also various internet resources that you can also look for in getting information about these things. Okay. So energy transfer can result from different interaction mechanisms. Interactions can be Coulombic and or due to intermolecular or orbital overlap. So, both mechanisms can be operative. That I just wanted to mention, that both mechanisms can be operative. Coulombic interaction consists of long range dipole-dipole interaction, which is called the Forster mechanism, and the interaction due to intermolecular orbital overlap, which include electron exchange, that is a Dexter mechanism, and charge resonance interaction at short range type these are all short range type. So, so these are the two prime mechanism, and for singlet energy transfer, both types of interactions can be possible. I mean Coulombic as also intermolecular orbital overlap type of thing, because for singlet to singlet interaction, I mean the separation is not that large. So, it is in that case you can think of orbital overlap as well. But for triplet energy transfer, I mean, this can be due to orbital overlap, I mean only due to orbital overlap, and that is a Dexter type of mechanism. So, singlet energy transfer interaction may be Coulombic or may be intermolecular, but in case of triplet interaction can be, I mean, due to orbital overlap, or called the Dexter mechanism. So there this you know, like finishes the discussion of I mean, this discussion never ends, I mean, this energy transfer issue, because it is so important and so many variety of examples are available in literature. So that, I mean, if one starts to speak about it, I mean, with various different examples, then it may be a never ending thing. Anyway, this I mean, this is a preliminary preliminary, you know, discussion, or maybe you can say that it is an introductory discussion. So if time permits, then maybe at some later point of time we can take some specific examples or interesting example and discuss this, I mean, with respect to these issues. Okay. Now next we will move on to electron transfer, and especially when we deal with electron transfer, we generally, I mean, deal with electron transfer and also fluorescence, then it is the photo-induced electron transfer phenomena that always comes into our mind. Now electron transfer, like you heard about this various examples, like say some redox reaction in solution, so oxalic acid and permanganate reaction. Okay. So it is a redox process, and it occurs in solution. So, but this reaction occurs in the ground state. Okay, that means both the reactants are in ground state, and if you consider from the point of view of this free energy of the process, then if you calculate, then you will be finding that its free energy change for this initial state to final state, permanganate, oxalic acid, then right hand side, so Mn2 plus and other products. So if you consider and calculate, then you will be finding it has got a negative delta G. Therefore, it is a spontaneous process. Of course, some experimental conditions are needed to be you know, controlled or needed to be maintained. So so that is a ground state electron transfer. Okay. So and many other examples can also be found in I mean, like if you think of electrochemical process, I mean reaction in a cell. Okay. So you have got two electrodes, and you have got you know, right hand compartment, you have got left hand electrode compartment, and then you know, this compartment, in these individual compartments, you know, redox reactions are taking place. I mean, in one compartment there is oxidation, in other compartment there is reduction. So electron transfer is happening. Okay. Electron transfer is happening like in our this electron transport chain in the mitochondria, I mean this respiration cycle. So in that case, I mean ATP to ADP or ADP or some other reaction. So in all the cases, you know, this electron transfer, I mean there are various places where you will be finding that electron transfer is the key mechanism for some chemical reaction, and these are of immense importance. Okay. Now in photo-induced electron transfer, it does not happen in the ground state. So whatever I mean you can think of is that you need to have a photo-excited system, and then I mean then when it is excited, the various reaction may take place, that is called your photo-induced processes. I mean energy transfer as just which we just have finished. So that is also a you know, photo-induced process. I mean because you excite your donor, and then energy is transferred. So, this energy transfer normally it does not take place in those cases. I mean, whatever examples we have taken there, in those cases it does not happen in the ground state. So, in the excited state that transfer happens. So, photoinduced electron transfer is one of the most important processes in photosynthesis. Okay. Then photoimaging, organic reaction, optoelectronic systems. Optoelectronic system means where, I mean, when you shine your device or the sensor with light, then some current is generated, and that current switches I mean some of the other circuits, so that some process is started or some process is stopped. Okay, like in photoinduced process, if you think of like in photomultiplied tube, when photoelectrons are ejected as a result of incidence of fluorescence photons. Okay, so like in photo devices. Okay, so photoelectrons are ejected. So, but basically in that cases photoelectrons are ejected, and if there is some receiver, then that can be taken. So, it is basically a photoinduced electron transfer from the photocathode to the anode. Okay, so this photoinduced electron transfer is one of the most important processes in photosynthesis, photoimaging, organic reaction, and optoelectronic devices. So PET, photoinduced electron transfer is PET, or in some books you will be finding PIET. So, photo-induced electron transfer, PET. Okay. So, exploration of PET in artificial systems or some model systems should lead to further understanding of the biological processes responsible for various phenomena in living system. Okay. Now, light induced electron transfer is a process in which an electron is transferred from an electron donating species, which is called the donor, to an electron receiver, which is called the acceptor. So, prior to electron transfer, there is excitation of donor by light. So that is photoinduced, that's what is called photoinduced. So before the electron transfer is taking place, you need to have this donor to be positioned in the excited state, so that it will be easier, or it is now suitable or energetically suitable situation to transfer the electron. Okay. So, electron transfer. So, from that electron transfer quenching, that term is coming. That is why we called electron transfer quenching, that if you do not have any acceptor, okay, or any if you do not have anything else other than this D star, then D star, if D star is emitting, then you should, or you can expect emission from D star. So, you will be getting some amount of fluorescence emission, this fluorescence photons you will be receiving. Okay. But the moment you add something, some quencher, that is electron transfer quencher, then this electron transfer quencher will accept one electron from the donor, so that it will go to the what will happen, let me say D star plus acceptor. So that suppose there is a pair of electron, so this electron will come over here, so that you will be getting D, this plus dot minus A, and this is called this radical, this is radical cation, this is radical anion. So, this is radical ion pair. radical ion pair. Okay. So this quenching is your via photoinduced electron transfer. Okay. So the process, I mean, the first one is your charge transfer, d star plus a, d plus dot plus a minus dot. Electron transfer, I mean, this electron is this is also an electron transfer or charge transfer. Why I say? Because in this case a hole is created over here and an extra electron comes over here. Okay. So this is your charge transfer. The second one is the electron transfer, that you have got d minus dot, then this dot, I mean this dot is say transferred to here, of course maintaining the proper energetics and other factors. If it happens, then you will be getting d plus a minus dot. Okay. So that is your electron transfer. So electron is transferred, and the third one is hole transfer or plus transfer. So in that case you have got this d plus dot, then a, giving rise to d plus a plus dot, so that this plus is, I mean basically plus is transferred. So three things I mean you can think of, you can consider. One is charge transfer, another is electron transfer, third one is hole transfer. So here this light energy is converted into electrochemical energy. After the electron transfer process, a charge transfer state is created. So immediately after this, so this together, I mean, although it is called a radical ion pair, it is called, I mean you can have a charge transfer state. Okay. So you have, if you energetically you have an energy diagram, then this may be your I mean in between it may be like you go to a charge transfer state, so that electron is basically transferred to a, and as a whole this d plus dot a minus dot as a whole as a combination is a charge transfer state, which is basically a dipolar state. You see that plus minus, it is a dipolar state consisting of radical cation from the donor and a radical anion of the acceptor. So this you can think of. Okay. The charge transfer state created can undergo many different processes, like when the charge transfer state is created in a solution in a solvent cage. So what is happening, that you have your donor and acceptor, that these two are coming under the same solvent cage, then electron transfer takes place. So that you have this one is plus, another is minus. So like this you have inside the cage. Then what is happening, that possibility is that back electron transfer may take place. So that back electron transfer takes place means it is called a recombination, or the solvent cage will penetrate through the space, I mean between these two counterparts, so that this d plus dot and a minus dot will separate. So this is called the solvent separated radical ion pair or solvent separated radicals, and ultimately they will go at some place. Okay. In the photosynthetic reaction center, after the energy transfer from light harvesting system to a special pair, a first electron transfer from this special pair to porphyrin, I mean pheophytin P in 3 picosecond. It occurs in 3 picosecond. Then it is followed by the second electron transfer from this P minus dot to UB quinone QA in 200 picosecond. Okay. Next, this electron is transferred from QA to another quinone QB in 100 microsecond. So these are the different time course of the event. Okay. In the ultimate state, QB takes up 2 protons after 2 electron transfer cycle and leaves its site, traverses the membrane in which the system is initially located, and release protons again. Okay, and hence a proton coupled electron transfer is completed. Thus light energy is converted into an electrochemical proton gradient, okay, and by which the biosynthesis of energy rich molecule like adenosine triphosphate takes place. So, this way energy is harvested, okay, in the form of energy rich molecule adenosine triphosphate. Okay. In another case, the making of a snapshot, I mean this photography, think of this earlier, I mean nowadays it is your this digital technology is different, but you know, earlier it was like film technology, where you know, when you take snapshot, the key step is also the light induced electron transfer. The charge transfer state so formed is trapped by defects of crystal or imperfections of the crystal in silver halide crystals, and chemical developing, I mean using this hypo etc. solution of the photo leads to the formation of silver cluster, and ultimately you know you get the photograph. So, this, you know, diagrammatically it is you know, D plus A, this starting ground state, then it is your D star plus A, which is the locally excited state, okay, and from this locally excited state it may give rise to emission EM, okay, or this locally excited state may undergo electron transfer. If other factors are favorable, then if your energy requirement is, you know, fulfilled, then I mean thermodynamics is fulfilled, then D plus dot plus A minus dot is created, which is called the charge transfer state, CT state. Okay. Now, this CT state can have various reactions, I mean possibility. One is a recombination, I mean back electron transfers, which is also called the reverse electron transfer, RET or BET, okay, BET or RET, reverse electron transfer. So, here this back electron transfer can be radiative or non-radiative. So, in that case, when this D plus dot and A minus dot combine, then maybe in some cases you can get photons, or maybe in other case you can get heat, but they will recombine, this back electron transfer will take place. So, these are the possibilities, I mean in one sense, or maybe it can do some other reaction, like say some bond breaking or bond formation. Supposing this charge transfer state is prone to some chemical reaction, so it will undergo further reaction to give you products. It may be bond breaking, or maybe new bonds are formed, okay, or maybe some other processes, like say 2 electron transfer, like say D plus dot transfers another electron to A minus or A minus dot. So, then what is happening, that in that case you will be getting D 2 plus dot dot, and I mean maybe or maybe no dot will be there, just D 2 plus, and here A 2 minus double dot, okay. So, the second one is a diradical, okay, I mean this A dot dot can be a diradical, okay, or maybe the other one, that is D having 2 holes, okay, it is like that, okay. Now, the first electron transfer reaction studied was self-exchange electron transfer reaction in inorganic ions in aqueous solution. The understanding of organic charge transfer complexes started by Benesi and Hildebrand in 1949, who observed a new absorption band in solution of aromatic hydrocarbon and iodine, and introduced the idea of charge transfer in the ground state. The Mulliken model for electron donor acceptor complexes and the discovery of XMA formation by Foster and Casper in 1954 were the essential steps led to the development of the understanding of electron donor acceptor system. Okay. So, it is the Jablonski diagram. So, you can get I mean more information on these, I mean from this thesis. Actually, this was taken from this this thesis. Anyway, so Jablonski diagram for electron transfer as one of the decay pathways for the first excited singlet state. First excited singlet state is given by this, you know, like here you see that this is your S0, this is your S1 state, and it is the photo excitation. Okay. Now, excitation to this higher level, this is your S1, then vibrational relaxation, this is called your IC, and this is you know, fluorescence. Okay. And this is ISC. So, this is electron transfer, and ultimately you will reach this charge transfer state. Okay. And the emission what you get is your this is your charge transfer emission. Okay. And this is your phosphorescence emission, this is your fluorescence emission, and this charge transfer state basically in some cases give rise to charge transfer emission, or in some other cases the charge transfer emission is not there, just non-radiative decay to the S0 ground state. So, various processes may take place when you consider this donor acceptor pair, and in which the donor is excited with photon, then electron transfer leading to charge transfer state, followed by, you know, various processes as I told, you know, you in the earlier slide. Thus, the occurrence of electron transfer should diminish both the emission quantum yield and lifetime. So, if you go back to this slide, you see that some of the population, I mean fluorescence intensity will depend on what, on the population in the excited state. So, if some population is transferred to here, then rate of, I mean deactivation, this radiative deactivation or whatever you call, I mean radiative deactivation, I mean the population over here will be diminished further as a result of this process. Therefore, ultimately what you get, that you will receive, I mean you will receive less photons over here, less number of photons, because some of the energy is over here, or the branching is over here, I mean the excited population is branched to here. So, as a result of which your population density will decay faster. So, therefore, this both emission quantum yield, that is emission intensity, and lifetime will be diminished. Other mechanisms that can be responsible for fluorescence quenching will be like energy transfer, which I already have discussed. Another very important thing is proton transfer. Proton transfer, then maybe hydrogen bonding. Hydrogen bonding in some cases may be responsible. Then external heavy atom effect. Heavy atom effect is also responsible for fluorescence quenching, because external heavy atom, what it does is it induces this singlet to triplet evolution, I mean singlet to triplet transition, because of this spin orbit interaction, and therefore net this singlet S1 population is diminished, and as a result of which your fluorescence quantum yield and also lifetime is diminished. So, that is why I mean fluorescence quenching, that can be due to various facts, various phenomena. One is like what I just have started to discuss is electron transfer, the other could be energy transfer, proton transfer, hydrogen bonding, etc., etc. So, this proton transfer topic I will take up maybe in some other lecture, but just I give you the idea what is exactly happening over there. So, excited state, why in the excited state your this electron transfer is taking place? Because in the excited state, you know, in the ground state electron is over here. Okay. So, electron is over here, two electrons are there, So you know, this is your vacuum state. Okay. So this is your this process is reduction, this process is, say if this is oxidation. So oxidation means ionization, and electron affinity means you are adding electrons. So you see that ground state, this is occupied, I mean this HOMO is occupied, LUMO is filled up, and in the excited state, I mean if one situation is there, then your reduction will be, I mean electron will come from vacuum state to here, I mean over here. Okay. So and this gap is basically delta E star. So you see that electron affinity and ionization potential. So if it is in the excited state, then ionization potential, you see that it is easier to ionize from this LUMO state, but if it is in the ground state, you need to ionize from here. Okay. So that's why in the excited state, this acts as a, sometime it acts as a better, you know, electron donor, because it is already, I mean energetically it is somewhat in the above, I mean it is above the ground level. So this much of energy is not required. So you can simply transfer it to some receiver. So in the same way, I mean oxidation and reduction, this phenomena is drastically affected if you consider excited state, or if you start with excited state. So that's why in a photo-induced electron transfer or photo-induced charge transfer, sometimes is easier, or energetically it is favorable. So that's why in a photo-induced electron transfer, sometime, I mean if you consider a reaction which does not occur in the ground state, but if you excite one of them appropriately, if you excite this pair, then you can find that the electron transfer or the redox process has taken place. So that's why it is very important. So free energy of gas phase electron transfer, I mean you can say like this, I mean whatever, this is your D plus A, it is the ground state, this is in the D, from the D star state. So if you consider this diagram, it will be clear from here. So delta G is IP minus EA, and here it is IP minus EA minus delta E star is the energy required to excite, I mean energy required for this excitation. Okay. This is your what I already have discussed is Coulombic mode and exchange mode of transfer. This is electronic energy transfer, I mean what I just have discussed. So I discussed a few minutes back. Anyway, so basically this is electron exchange process. You see, this is an electron exchange, even if it is electron transfer or energy transfer, whatever it is an electron exchange process here. And in case of Coulomb, it is a long range interaction. Okay. So electron transfer by non-emissive mechanism. So it is basically an electron transfer, although you are generating the excited state. I mean in principle you are generating, I mean you are transferring energy, the electronic energy, by means of electron exchange or Coulombic, but it is it is via electron transfer, and as a result of which the electronic energy has been exchanged. Anyway, so that's why electron exchange or electron transfer is important also. So the processes which, so that's why it is important to mention that processes which occur by electron transfer. Okay. So electron exchange process is, one is energy transfer. So here you see that in this mechanism the energy transfer occurs, but this is electron exchange. In one case it is here it is Dexter mechanism, so electron exchange is taking place. So then triplet annihilation, then charge transfer and charge translocation. Okay. So basically this transfer and translocation, these are similar term. So so basically what is happening that through electron transfer, I mean charge transfer is taking place. Anyway, so basically electron exchange process is important, and therefore it should be, I mean should be dealt with in more detailed fashion. Okay, so electron transfer process, I mean simple models, then we'll deal with Marcus theory. So that will be taken up in the next next class. So far whatever we have learnt over here is that we have learnt this a new mechanism of energy transfer, that is your Dexter mechanism, and then we started with started discussing about why photo-induced electron transfer is important, since we deal with photo-induced processes. So that's why it is important. So these are the things that we just have started with. So in the next lecture we'll start discussing this theory of, I mean Marcus theory of electron transfer, and other associated issues. So till then, thank you.